Hello, this is problem set number 4, problem 5. You build a heat engine that takes 1 mole of an ideal diatomic gas through the cycle shown in the figure. Part A, show that the process AB is an isothermal compression. Okay. Let's write down some of our givens. It's given that we have a heat engine. That we have N equals 1.00 moles of an ideal diatomic gas. Okay. What else is given? Well, let's look at our PV diagram to the right. We know that at state A, we have a pressure at A of 2 times 10 to the 5th pascals. The volume at A is equal to 0.010 cubic meters. At B, the pressure is 4 times 10 to the 5th pascals. And the volume at B is equal to 0.005 cubic meters. And the pressure at C is equal to 4 times 10 to the 5th pascals. And the volume at C is equal to 0.010 cubic meters. Right? And I just got all that info from the PV diagram right here. Okay? All right, so part A, show that the process AB is an isothermal compression. Okay. So I will use the ideal gas law to do that. Which is PV equals nRT. Okay. So using this ideal gas law equation, if I wanted to find the temperature at A, that would be equal to the pressure at A times the volume at A divided by the constants N and R, correct? And likewise, the temperature at B would equal to the pressure at B times the volume at B divided by the constants N and R, right? Since these guys are constants, the value in our denominator for both TA and TB are equal, right? So all I care about then is if PA, VA is equal to the pressure at B times the volume at B, then the process AB is isothermal, right? As long as the value of my numerators are equal. So let's find out if that is indeed the case. Okay, so is the pressure at A times the volume at A equal to the pressure at B times the volume at B? Okay, we don't know that. Let's find out. So pressure at A is, sorry, there seems to be a delay in my stylus's writing. So the pressure at A is 2 times 10 to the 5th pascals times the volume at A, which is 0.01 cubic meters. Is that going to be equal to the pressure at B, which is 4 times 10 to the 5th pascals, multiplied by the volume at B, which is 0.005 cubic meters. Okay. And if I plug that in the calculator, I would get the answer is 2,000 pascals times cubic meter on both sides, right? Which, by the way, pascals times cubic meter is equal to joules. So we get 2,000 joules is equal to 2,000 joules. So yes, temperature A is equal to temperature at B. So because the temperature at A is equal to temperature at B, then the process AB is isothermal. So therefore, therefore, TA equals TB. So process AB is isothermal. Okay? That is part A. If you guys want to know why Pascal times cubic meter is equal to a joule, well, a Pascal is the same unit as kilogram over meters times second squared, whereas a joule is equal to the unit kilogram times meter squared over second squared. Okay? So here when we multiply the Pascal by a cubic meter, the meter in the denominator would cancel out and we would get meter squared in the numerator. So that would be a joule. All right? Okay, now part B. So part B, during which processes of the cycle is heat absorbed by the gas? Okay? And during which processes is heat rejected? By the gas or system. Okay? So if you guys see me use the word gas and system interchangeably, that's because the gas is the system. So, and then the other question is, during which processes of the cycle is heat rejected or released, right? Rejected by the gas. Okay? So I can answer that through, well, when was heat, how do you know if heat is absorbed or heat is rejected? Then we'll have to go back to Q, which is our heat transfer, right? So Q is positive when heat enters the system. Okay, and it's negative when heat leaves or is rejected the system. Okay? When heat leaves the system, it's negative. All right. So let us figure out for process AB. Okay, that's an isothermal process, right? So let's use the first law of thermodynamics, which is the change in thermal energy is equal to heat transfer minus work done by the system. Okay? Remember, in an isothermal process, there's no change in temperature. So delta ETH would be 0. That's a change in thermal energy, which would be 0 if there's no change in temperature, right? So therefore, Q would be equal to work done by the system, right? And recall, for an isothermal process, so this is only true for an isothermal process, right? Work done by the system is equal to nRT times the natural log of V2 over V1, right? So my Q would be equal to the work done by the system, which is equal to nRT times the natural log of VB over VA, okay? We do not know what is the temperature at AB, so let's figure that out. We do know from part A that TA equals TB, so for all side missions, we're going to use brown ink, okay? So side mission number 1, find out TA and TB temperature. So we said that TB equals PBVB over NR, right? And we said that PBVB was equal to 2000 joules divided by N, which the problem said was 1 mole, and R, which is a constant that everybody should know or have in your cheat sheet, that's 8.31 joules per mole times Kelvin, right? Okay. So if we do that, we would find out that, oops, that should be brown. TA equals TB, right? Because that's what we found out in part A, which is equal to, plug that in your calculator, cancel out the units, is equal to 240.67 Kelvin, okay? All right, now back to our original problem. So let's plug in the values here. N is 1.00 moles. R is 8.31 joules. Nope. 8.31 joules per mole times Kelvin. T, we just solved inside mission number 1, right? Right here. That is 240.67 Kelvin times the natural log of the volume at B, which is given in the PV diagram, 0.005 cubic meters, divided by the volume at A, which is 0.010 cubic meters, right? Okay, if you plug that in your calculator and cancel out the units, we would get that the answer is equal to, again, this is for state A to state B, process AB, right? So QAB is equal to negative 1,386.3 joules, okay? And so since we have a negative number, right? Negative value, therefore heat is rejected by the system, okay? So for process AB, heat is rejected by the gas, okay? So now let's look at process BC. Okay, process B to C. process BC is isobaric, right? Because if you look at the PV diagram, the pressure is constant from state B to state C, right? So recall for isobaric process, so this is only true for the case of isobaric process, okay? Q is equal to N times the molar specific heat for constant pressure times the change in temperature, okay? So that is only true for an isobaric process. So let's use that. Before we use that, we're not given CP, right? But we should know that we should know this from our notes. So if you don't have this, please have this in your notes, that the ratio of molar heat capacity, gamma, is equal to the molar heat capacity for constant pressure divided by the molar heat capacity for constant volume. So CP over CV. All right. And so we could say that CP is equal to gamma CV, right? Also know that gamma, or the ratio for molar heat capacity for a diatomic gas, value is 1.40 for a diatomic gas. Okay? All right. So now back to our problem. We'll instead of using CP, right, since we're trying to figure out Q, which is N CP delta T, I'm going to substitute CP now, so it will be N times gamma CV delta T, right? I guess we should also know that this also comes from the notes in the book, that for a diatomic gas, the molar heat capacity for constant volume, CV, is equal to 5/2 times a constant R, okay? Again, this is for a diatomic gas. Okay, so now we know everything. And these things you just have to have in your cheat sheet, or you have to know it off the top of your head, right? And because the problem stated that we have an ideal diatomic gas, that's why I know to use these values, 5/2 R and 1.40, okay? So it's very helpful to have these in your cheat sheet. All right. So N, right, is 1.00 moles. Gamma for a diatomic gas is equal to 1.40. CV is equal to 5/2 R, right? And R is just a constant, 8.31 joules per mole Kelvin. And you should already know the value of R at this point, right? You should have that already. Delta T, what is the temperature at C? Actually, we don't know the temperature at C. So let's do a side mission. We know the temperature at B. We don't know the temperature at C right now. So side mission number 2. Okay, this was side mission number 1. Now it's side mission number 2. Okay, to get the temperature at C, it would be again, we would use the ideal gas law, PV equals nRT, right? But I'm interested now in the temperature at C, so that would be equal to the pressure at C times the volume at C divided by the constants N, R, right? And according to the PV diagram up here, the pressure at C is equal to 4 times 10 to the 5th pascals. The volume at C is equal to 0.01 cubic meter. and the value of N is 1.00 moles, right? That's given in the problem, and R is a constant, 8.31 joules per mole over Kelvin, okay? So plug all that in your calculator, cancel out units, remember for pascals right here. Instead of writing it as pascals, write it as kilogram over meter times second squared, okay? And then if you multiply that by a cubic meter, you'd get a joule. We talked about that earlier. And so your final answer, you would cancel out units, and your final answer, you would get the temperature at C is equal to 481.34 Kelvin, okay? All right, so now we can go back to our problem after completing side mission number 2. Delta C is the temperature at C, which is 481.34 Kelvin, minus, I'm going to move this a little bit to the left because I have no more space. Okay, so that's 5, that's joules. Okay, oh, no, minus the temperature at B, which is 240.67 Kelvin. Okay. And so now if I plug that in the calculator, cancel out all my units, I would get that again, this is for process BC, right? So the heat transfer from state B to C is equal to 6,999.89 joules, right? And since the value of my heat transfer is positive, therefore heat enters the system. Heat enters the system. At BC, process BC, okay? All right, and then the last part of the problem for process CA, that's isochoric, right? So we're going to use the first law again, which is delta ETH, or the change in thermal energy, is equal to heat transfer minus work done by the system. Okay, so let's look at the isochoric process. The work done by the system is the area under the curve, and we see that from C to A, it's an isochoric process, so that's a straight vertical line. In other words, there's no area under the curve, so work is 0, okay? So I'm going to cancel out the work here to 0. So now I know that my heat transfer is equal to the change in thermal energy, right? And recall that for all processes, meaning isothermal, isobaric, isochoric. Oh shit, why did I write isothermal? I meant to write for all processes. For all processes, the change in thermal energy is equal to N times the molar specific heat for constant volume, or molar heat capacity for constant volume, and multiplied by the change in temperature, okay? So I'm gonna plug that in for my Q. That is equal to N CV delta T, okay? So now I know my delta T, I know my temperature at C, my temperature at A, I know the value for CV for a diatomic gas, right? So N, that's 1 mole, times CV, which is 5 over 2R. So 5 over 2 times 8.31 joules per mole Kelvin, times delta T, which is the temperature at C, 481.34 Kelvin. Or sorry, no. Because I'm going from state C to state A, I have to use the temperature at A first, my final temperature. So the temperature at A is 240.67 Kelvin, right? That's the same as the temperature in B, minus the temperature at C, which is 481.34 Kelvin. All right, and if I plug that in my calculator and cancel out my units, I would find out that my heat transfer from process CA is equal to negative 4,999.92 joules. All right, and because the value of my heat transfer is negative, therefore heat is rejected or released by the gas or the system. I'm using gas and system interchangeably for process CA. Okay. So again, to answer the question in part B, during which process of the cycle is heat absorbed by the system, then the answer is the heat is absorbed by the system during the process BC, right? Because we have a positive value for our heat transfer. And heat is rejected by the gas or the system in process AB, since we have a negative value, as well as in process CA, because of the negative value as well. Okay? All right, so now let's move on to part C. What is part C of the problem? The temperatures. Calculate the temperatures at points A, B, and C. Guys, great news. We already did that. That was our side mission in part B to figure out heat transfer. So pretty much that's the answer for that, right? TA equals TB, which is equal to, we calculated that as 240.67 Kelvin. And the temperature at C we calculated as 481.34 Kelvin. Okay, so that's our answer for part C. Nice, we did that calculation in part B, side missions. All right, now what about part D? Part D, let's calculate the net heat exchanged with the surroundings and net work done by the engine in one cycle. Net is just another word for total, right? So calculate the total heat exchange or heat transfer with the surroundings and the total work done by the engine in one cycle. Okay, so guys, to do that, you know what? I'm just gonna use, so we're looking for Q total or net Q, and work total or net work, right? Let's use the first law of thermodynamics, which is the change in thermal energy is equal to heat transfer minus work done by the system. Okay? Guys, remember, this is from chapter 20, section 2, okay? When we discussed heat engines. For a closed cycle device, this is S, closed cycle device, or a heat engine, right? Because a heat engine is a closed cycle device as well. The the change in thermal energy is always equal to 0, all right, at the end of each cycle. At the end of a full cycle, okay? So, because that's the case, this becomes 0, right? And so I'm left with Q total equals my work total, right? Or the total work done by the system. And we already calculated actually the Q total, right? Because Q total, the net heat transfer or total heat transfer, that's just going to be equal to the heat transfer in every process. So heat transfer from process AB plus heat transfer from process BC plus heat transfer from process CA. Guys, another great news for you. We already calculated that in part B. Here. Okay. So let's just plug those values in right now. All right. So for heat transfer from AB, we got minus 1,386 joules. Sorry, 1,386.3 joules. Okay. Plus the heat transfer from process BC, which was 6,999.89 joules. Then plus the heat transfer from process CA, which was negative 4,999.92 joules. Okay? And if you plug that in your calculator, you would find that the net heat transfer, or Q total, is equal to, right, is equal to the work total, or the net work. That's what we figured out up here, right? Because for a full cycle device, or for a closed cycle device, change in thermal energy is equal to 0 at the end of a full cycle, right? So then the net heat transfer is equal to the net work, which is equal to, plugging this in the calculator, 613.71 joules. And that's our answer for part D. All right. And part E, last part, it wants the thermal efficiency of the engine. Okay, so what is the thermal efficiency of the engine? Recall from our notes, thermal efficiency is equal to work out divided by QH, okay? And work out is the total work done by the system for each cycle, per cycle, okay? And we got that up here. We calculated that in part D. So that is equal to, so the efficiency is equal to 613.71 joules divided by QH. What is the hot heat transfer? For a heat engine, that would be when heat enters the system, right? Because for a heat engine, the hot temperature will enter with a QH, with a hot heat transfer into the system, right? So we would use QBC, which is when the heat enters the system. Why? Because the value for Q is positive. So that's what we need for a heat engine, right? All right, so then for QH, we would write down 6,999.89 joules. Okay, and I plug that in my calculator, I would find that the efficiency is equal to 0.08767 or 8.77% efficiency. All right, and that is the answer for part E. I hope that was clear. I tried to speed it up a little bit because my videos have been getting long. All right.